Hi. So let's take a look at problem 10 this Saturday morning. So we are dealing with the curve y squared equals x to the third. The real part I believe goes like this. Having a horizontal half tangent at 0.0. So we need to show that we get an addition just like at an elliptic curve. And then we have to prove an isomorphism with the additive group of complex numbers on this curve minus the 0.0 point, but including infinity, it seems. And then he writes about a limit process. I think we should look at that first. So if we look at the curve y squared equals 4x to the third minus d3, so it has one real root, e1, and then it goes like this. And then to find the value of omega 2 and omega 1, we need to take omega 2 at least. We need to take the integral from e1 to infinity of 1 divided by square root of the derivative. That seems very easy. From some lower bound here, that's never mind, to infinity of 1 divided by the square root of 12x squared So we need to state what the limit is, because it's the cubic root of d3 divided by 4. So this becomes infinity, and as as the upper bound goes to naught, the other one becomes minus infinity. So if we take these integrals for each value of d3, letting d3 tend to naught, then we have an increasing. It's actually the same integral with increasing bounds. You know what? This is very weird, because I I get an infinite omega 2 in this case, which I shouldn't have. Because this polynomial has 3 roots, one here, and one here, so it should work fine. So I guess I've made a mistake here. This is really serious. All my previous work, I have done this integral from E1 to infinity, and it has been lovely and finite, no problem. So what's wrong here? I need to take a break and look at that. That was easily found. I took one look at the problems of the last section, and then I could see it. Down here we need to have the polynomial itself. So that was what I could delete. So we can't do this one, of course, but when g tends to naught, this is an increasing sequence of functions. So it goes upwards towards 1 divided by square root 4x to the third, 1/2 x in minus 3/2. So, and this in the integral of this we can compute. And of course, the function we actually are working on, it goes like, it's naught, I'll just make it red. It's naught from 0 up to here, and then it goes like this. And as E1 tends to naught, to the left here, this one extends, so we have an increasing sequence towards this. And that means that by the monotone convergence theorem, they are positive and increasing, so lovely. Tends to the integral from naught to infinity minus so I get that's x to minus 1/2 if we take the derivative of this guy, we get minus 1/2 x to minus 30 to minus, and then put in the limits, 0 to infinity. At infinity it gives 0, at 0 it gives infinite, so it's infinite. So the monotone convergence theorem gives that omega 2 will tend to infinity, and that must be the same with the other roots, of course, as well. All right. So as d2 and d3 approach 0, yes. We can believe that. Now back to this curve. Addition, we can either do it in its own right, writing up the addition formulas and then reducing it by setting a equals to 4, b, c, 0, and d to 0. So, and then see what happens. But then we have the problem with associativity. I don't think the formulas will reduce much, because the only constant except a that occurs is b. So it's only one term in the addition formula that will cancel. So I tried actually when I read the paragraph to prove associativity by raw computational power, but it was totally intractable. So I couldn't do that. So I guess I can't do it in this case either. So we'll use the limiting process and say that on these curves, as G3 tends to 0, on each curve we have addition, and then we shall have a limit of a point on this curve to a point on this curve, and then define the sum as the limit. So that's my program. So given a point here, I want to define a function on this curve so that it approaches. And we can do that for small enough E1s just by choosing the same x value. So we wait until E1 becomes less than x, and then we just take the x value here. And that means if we have to add 2 points, and then say this one, then we add the 2 points on this curve, and then let G3 tend to 0. We have to show that the limit exists. So let's start with 2 points with the same x value. Then they will come with opposite y values, so the sum is infinity. So that's it. Now if they have different x values, we'll have a sum on the curve. So we'll just write it up. Maybe I'm being too thorough in this, but then we can explicitly see that it converges. I'll say that's negative. And then we write up the sum. And I need to find the formula. Here it is. And that's assuming they're different. That's 1 divided by a, which is equals 4. And then b minus y divided by a minus x squared. And as g3 tends to naught, the limit is clear. This is 2, the x value, that's just x. And then b, that tends to minus 2. A to 3/2 divided by plus 2. Oh, minus the y, that's plus 2. X to 3/2 divided by a minus x. Any reduction possible here? It doesn't seem likely, does it? Well, that might be, but leave it for now. So that means that the limit exists. And then the associative law follows from the limit theorem and, of course, commutativity as well. So the same geometric procedure, smooth point of the curve. What's actually wrong with 0.0? I don't see anything wrong with that point, really. But never mind, we exclude it. Show that the map takes the point, gives an of the additive group of complex numbers. So we have to consider this a complex, this as a complex projective curve. And then we map x to x divided by y. So we have to see the original points, these 2 points, they map to what, and the result maps to what. So I need to reduce this. And doing that by hand, I'm sure to make that wrong. We have some experience with that. So I'll just put it into Maple and see what it gives. And then the y value I'll compute in Maple as well. And then we can see what the fraction of the two y and x, new y and x values will become. So another break, and then I shall have prepared the Maple documents when I return. When typing into Maple, I realized that I actually had to set a equal to 1 to get the curve we actually want, which was y squared equals x to the third. So a should have been 1. So this is what Maple told me. So we assume x and a is positive, set y to the values. Oh, actually y should be negative, but never mind. Let's have two positive values. Then I define the sum, and from that we can divide the y value of the sum, and then we take the proportion, the x value divided, so it maps to this in C. And we need to reduce this. This is weird because actually we shouldn't use this at all because we're working with complex numbers. Well, we'll handle that afterwards. Now, this can be reduced. Now, how do we do that in Maple? I think we set a to the square of something. And the same with x. And then we call this something. Oh, e, never mind. That's a warning I'm not interested in. No, then let's use f instead. So no warning. And then simplify t. It won't do it. So let's do it the other way. Now we set x to d squared and a to f squared. Invalid base. Ah, damn it. That was a... Why doesn't it perform the... Why doesn't it perform the substitution that I write? Let's start all over again. Oh yes. Oh my God, we get the right result. So this is, or do we? Now the original, so simplify, it was x divided by y plus b divided by a. Oh, and then we need the so the a was f squared, so that's f. X was d squared d plus 1 divided by x, which equals d squared. So, what have I done? This should of course agree with this. Oh, there's a little weird thing here. This map, we actually know the y value. X. So that gives minus plus and x 1 minus x to minus 1/2. So it's very simple. We don't need all that complicated. We could just have worked with the x values. So 1 divided by square root x Now, did I do this correctly? I'll just check. Minus x1 minus x2 minus b divided by a. That's formula 7.1 I'm using here. Plus 1 divided by a times the slope squared. The slope is by ax. So this one seems correct. And then when we just use x sum instead here, maybe I made a mistake in the y value. Yeah, that had to be minus, of course, but let it be for this, for now. And then 1 divided by, I'll just copy it. That was wrong. Square root a. and we do get the same. So that means the x values give the same, so we now just have to check the y values. So this means that the map that maps a point to the same sign as y the opposite sign of y in the real case, and then so it's a question of the branch we have to choose. Now, is there more we want to do to this exercise? I realize that I haven't really got any control over the branches of the square root I need to get the right result. So, of course, y divided by, or x divided by y is the good way to do it. So I haven't really proven it, that it's a homomorphism or an isomorphism. That's interesting, really. So I've shown that it's a homomorphism from the complex curve, the projective curve here, except this point, which I don't really understand why it's not taken into account, and then to the complex numbers. So I need to show that it is one-to-one, and I need to show that it's onto. This actually shows it's on one-to-one, and also onto, because this covers the two signs of the square root, the two branches of the square root, sorry. So it says onto. Well, that's how much work I'm prepared to do on problem 10. So it's a little fussy about the different branches of the square root when we compute y. And the addition formula doesn't have this fussiness, so it's my work that's fussy. But we'll just leave it at that. After a break, I'm back. It's now the middle of the afternoon. And first of all, I wanted to prove that I could actually handle the algebra that I stopped doing in the exercise. So here's the first part where I compute the sum, the x value of the sum, and then start on the y value, ending up with an expression that is reducible. And then just to prove that I actually can do the algebra. So of course I can't do it on a blackboard. That's just I don't have space enough on a blackboard to do it, and while I'm recording I don't have so many resources left that when I need to speak English, to say what I do in English, that I can do the calculations correctly. But then I got the idea to repeat the computation of the entire section. And the point is that we start with a function, a complex function, and you may wonder where that came from. And actually, if you look at the definition of Weierstrass P function, that's section, is it 4, 1. Yeah, 4, 1. The series defining the Weierstrass P function, and then the lattice expand towards infinity, then you'll just wind up with 1 divided by z squared. This was, of course, not how I found it. I solved the differential equation, but I don't always find the best way the first time around. Now, we then have the complex plane minus naught, and map it into f of z point the derivative. And we do it the same way in the book. This is a group, of course, without zeros, so we have to think about zeros separately. I discard this now, so just map this. And then the additive group on the complex plane, we want to see what it gets on this. And of course it's a 1-to-1 map, because this function is 2-to-1, and they have opposite derivatives. Like if z is unity, it went to, or plus minus 1, then it both goes to 1, and the derivative is plus minus 2, or minus plus 2. So it's 1-to-1. So the addition should give an addition on this curve. So, and we repeat the thing we do in the book, that we take 2 points with different x values. They have an equation of the form and then we look at the function we know that it has 2 zeros, and this function has a pole of order 3 at the center, so it must have 3 zeros, counted with multiplicity, of course. And that's because if we integrate 1 divided by x to the third, 1 divided by x, and a linear function, what's it called? A differentiable function, holomorphic function around a large circle containing all the zeros and poles, we get naught. So the number of poles and zeros are the same. So there are 3 zeros. We can know 2 of them, and then using the other theorem that now what was the function we should the lemma or it's the lemma on page 30. The function they work on is and we need to prove that the curve integral around a closed curve vanishes. But I'm sorry, does this happen? If we differentiate this function, we get So we have poles at the zeros, and the pole at 0 is of order 4 and of order 3. So there's a pole of order 1. But could this have some zeros? Oh, when we integrate around here, it's only the poles that matter. So this should vanish as well, I think. If you agree with that, then you will see that the sum of the three zeros on this function. Yeah, we have a pole of order 3, so three zeros. So the sum of the zeros vanish by the lemma, and therefore we have the map. So all we need to verify is that the map we have here it has an inverse map called x divided by y, which equals, I found out how to do this. So this is, the derivative is minus 2 set to the minus third. F of z is set to the minus second, so that's minus 2 divided by z. What am I actually about? Oh, it's the wrong way. It's x divided by its derivative. So this is I get minus 2z. All right, z. But the additive group the map set maps to minus 2z. That's an additive isomorphism. So this way we can solve it without all the problems I went through just copying the theory of the text. All right. So now I consider problem 10 solved.